We'll start in 1 minute. Today we'll start the test 3 review. Tomorrow we'll continue the review, and then on Friday will be test 3. And this first problem, identify the curves in the xy plane that are represented by the parametric equations and indicate the direction that the curve is traced as t increases. And then eliminate the parameter t and write an equation in terms of x and y. If we plot a few points, we'll pick some t values and find the corresponding x and y values. Okay, so x or t ranges from 0 to 2 pi. So we'll just start with 0, pi over 2, pi, 3 pi over 2, and 2 pi. And the x-coordinate is 0 because sine of 0 is 0. The y-coordinate of the first point is 3. Then when t is pi over 2, the x-coordinate is 2 times 1, or 2, and the y-coordinate is 0. When t is pi, the x-coordinate is 0. Cosine of pi is -1, so the y-coordinate is -3. Then at 3 pi over 2, sine of 3 pi over 2 is -1, so the x-coordinate is -2, the y-coordinate is 0. And then after one complete revolution, when t is 2 pi, the x-coordinate is 0 and the y-coordinate is 3. Okay, so plot those points in the xy plane. 0, 3, and then 2, 0. 0, -3. -2, 0. And then the terminal point is 0, 3, the same as the initial point. The path is clockwise, so we indicate by putting an arrow in the clockwise direction. Hey, this is supposed to be an ellipse. and then eliminate the parameter t. So one way to do it is solve for sine of t in this equation. That is, x over 2 is equal to sine of t. And in the other equation, solve for cosine of t to get y over 3 equals cosine of t. Then in each of those equations, square both sides. So on the left-hand equation, we have x squared over 4 equals sine of t squared. Square both sides of the other equation, we get y squared over 9 equals cosine of t squared. Then add the two equations together, x squared over 4 plus y squared over 9 equals sine of t squared plus cosine of t squared. But sine of t squared plus cosine of t squared is 1. So our equation without the parameter t is x squared over 4 plus y squared over 9 equals 1. And you'll recognize that as an equation for an ellipse centered at 0, 0. Okay, the next, part B, this time x is equal to e to the t, and y is equal to e to the negative 2t. T ranges from negative infinity to infinity. So we'll pick some t values and find the x and y values. Well, since x is equal to e to the t, this isn't the only way to do it, but one way to find x and y values is to pick t values in terms of the natural log. So a negative number is the natural log of 100. So if t is the natural log of 100, then x is e to the natural log of 100 or 100. And what's y? Well, we can think of y as, instead of e to the negative 2t, we can think of that as 1 over e to the t squared. And then if t is the natural log of 100, the y value is 1 over 100 squared, which is 10,000. So this point will be off the grid. But it's okay. Wait a minute, I'm sorry. The y value should be 1 over 100,000, or 1 over 10,000. Right? Because if the denominator e to the t is 100, 1 over 100 to the second is 1 over 10,000. Okay, let's pick some t values that are a little closer. How about the natural log of 1/10? The natural log of 1/10 is a negative number, pretty close to, well, it's the negative of the natural log of 10. And the x value is e to the natural log of 1/10 or 1/10. And the y value, 1 over 1/10, is 10, and 10 squared is 100. Okay, maybe just a couple more. Pick the natural log of 1. So in other words, when t is 0, the natural log of 1 is 0. So when t is 0, e to the 0 is 1, and 1 over e to the 0 is 1 squared, or 1. Okay, one more point. If t is the natural log of 10, then the x-coordinate is e to the natural log of 10, or 10. And the y-coordinate, 1 over 10 squared, is 1 over 100. Okay, so this won't be to scale. We do know the 0.11 is on the graph. And for a small x value, 1/10, the y value is 100. So that's way off the grid. So the graph is going to be something like this. The y-axis is a vertical asymptote. And then when the x values increase, the y values decrease. So out here at x equals 10, the y-coordinate is 1 over 100. Okay, let's eliminate the variable t. Well, if we use x equals e of t, and this other way that I wrote what y is 1 over e to the t squared, then we can just replace e to the t with x. So I get y equals 1 over x squared, or just 1 over x squared. But we should specify that x is strictly greater than 0, because e to the t, since x is e to the t is a positive number for all t. All right, moving on to the next one. Write parametric equations for the line in the xy plane that passes through the points 2, 1 and -1, -3. I'll remind you of a formula that you can use in general. A line through 2 points, x1, y1, and x2, y2. The parametric equations can be written for x. We can write x equals x1 plus the quantity x2 minus x1 times t. And the y-coordinate has a similar pattern, y1 plus y2 minus y1 times t. So in this particular example, using this formula, x equals 2 plus -1 minus 2 times t. And then simplify a little bit, we get x equals 2 and then minus 3t. Then for the y-coordinate, we have -1. Sorry, +1 is the y-coordinate that we're starting at. So 1 plus -1 minus 1 times t. So the y-coordinate is 1 minus 2t. Oh yeah, the y-coordinate. This y-coordinate is. So let's start over on y. So use the formula. y1 is 1, and then plus -3 minus 1. Simplify that, we get y equals 1 minus 4t. Okay, I think that works. So for all values of t between -infinity and +infinity, that will parameterize the line that passes through those 2 points. Okay, the next problem, find an equation of the line tangent to the curve x equals t to the second minus 1 and y equals t to the third plus t, corresponding to t equals 2. The point on the curve that corresponds to t equals 2. So when t is 2, the x-coordinate is 2 squared minus 1, or 3. And the y-coordinate, 2 to the third plus 2 is 10. Okay, that's the point on the curve that the tangent line is going to pass through. To find the slope of the tangent line, we want to find the derivative of y with respect to x. And we use the parametric equations. So dy dx is equal to dy dt divided by dx dt. Since y is equal to t to the third plus t, dy dt is 3t to the second plus 1, and in the denominator, dx dt is 2t. And then at t equals 2, the slope of the tangent line is the derivative evaluated at t equals 2. So the numerator, 3 times 2 to the second plus 1 is 13. And in the denominator, 2 times 2 is 4. Okay, that's the slope of the tangent line. So we can write the point slope form. Y minus 10, the y-coordinate, is equal to the slope 13/4 times the quantity x minus 3. Okay, that is a good enough answer for the equation of the tangent line. Okay, let's move on to the next page. Find the area enclosed by the curve x equals t to the fourth minus 4 and y equals t to the third minus 2t on the interval from negative square root of 2 to square root of 2. Okay, the parametric equation formula for the area enclosed. So this will be the definite integral from t equals alpha to t equals beta. G of t times f prime of t dt, where y is equal to g of t, and x is equal to f of t. Let's trace the curve a little bit before we compute the area that's enclosed. So we start at negative square root of 2. Okay, when t is negative square root of 2, and we raise that to the 4th power, well, that's like 2 to the 1/2 to the 4th, which is 2 to the 2nd, or 4, and 4 minus 4 is 0. So when t is negative square root of 2, the x-coordinate is 0. And the y-coordinate, t to the 3rd minus 2t, we can think of that as t times t to the 2nd minus 2, and replace t with the negative square root of 2. Well, inside the parentheses, the negative square root of 2 squared is 2. 2 minus 2 is 0. So the y-coordinate is also 0 when t is negative square root of 2. When t is negative 1, the y-coordinate, negative 1 to the 4th minus 4 is negative 3. Sorry, that's the x-coordinate, is negative 3. The y-coordinate, negative 1 to the 3rd is negative 1, minus 2 times negative 1. So we get negative 1 plus 2, or 1. When t is 0, the x-coordinate is negative 4, and the y-coordinate is 0. And just a couple of more points. When t is positive 1, the x-coordinate is negative 3. And the y-coordinate, 1 minus 2, is negative 1. And then at square root of 2, well, the same sort of thing occurs as with negative square root of 2. The x-coordinate will be 0, and the y-coordinate will also be 0. Okay, so if we trace this out, we're starting at 0, 0. And then the next point is negative 3, 1. Then we get negative 4, 0. Then negative 3, negative 1. And then finally 0, 0 again. So the curve is traced out counterclockwise. So this indicates that We're going to, if we compute the integral for the area enclosed, if we have limits from negative square root of 2 to positive square root of 2, the integral is going to be a negative number. If you want a positive number, you can take the negative of that, or you can integrate from the square root of 2 to the negative square root of 2. Or just remember, in the end, just take the absolute value of the whatever answer you get. But I'll just take the negative of the definite integral from negative square root of 2 to the square root of 2. And then we'll write down the formula for the integrand, or using the formula. So in the integrand, we have g of t, which is what y is equal to. So y is equal to t to the third minus 2t. And then we multiply that by f prime of t dt, where x is equal to f of t. So dx dt, we need to know that. It's just 4t to the third. So in the integrand, we write 4t to the third dt. I'll take this just a step or two further and leave the rest of it for you to do. So in the integrand, we just multiply the two polynomials, and we get 4t to the sixth minus 8t to the fourth dt. And this should be simple enough to evaluate. You can leave the result in raw form if you want. After you find the antiderivative, just replace this t with the square root of 2 in the upper limit and negative square root of 2 in the lower limit. Okay, the next problem, number 5. Find the arc length of the curve x equals t to the second, y equals t to the third minus t over 3 for t values from 1 to 3. Okay, so the arc length formula for parametric curves. So L equals the integral from t equals alpha to t equals beta, and the integrand is the square root of dx dt squared plus dy dt squared. Dt. Okay, so x is given in terms of t, and so is y. So first find dx dt, which is 2t, dy dt is 3t to the second minus 1/3. And in the next step, let's just find dx dt squared plus dy dt squared. And then after that, after simplifying a little bit, if possible, we'll put that inside of the square root in the integral. So dx dt squared is 4t to the second. And when we square dy dt, we're squaring 3t to the second minus 1/3. So we're going to get 9t to the fourth And then minus 3 times t to the second times 1/3 twice. So we're going to subtract 2t to the second. And then add 1/9. So in the next step, let's do a couple of things at once. We'll combine the like terms, 4t to the second minus 2t to the second, to get 2t to the second. But then we'll write it all with a common denominator of 9. So that means we multiply 9t to the 4th over 1 by 9 over 9 to get 81t to the 4th. And then 2t to the second times 9 over 9 is 18t to the second plus 18t to the second. And 1 over 9 already has a denominator of 9, so this is plus 1. And this is all over 9. Okay, both the numerator and denominator are perfect squares. So when we factor the numerator, we can write it as 9t to the second plus 1 quantity squared. And in the denominator, 9 is 3 to the second. So this perfect square is going to go inside the square root when computing the arc length. So the arc length is the integral from t equals 1 to 3 of the square root of this perfect square. So the square root of a perfect square, that simplifies pretty nicely. We're going to get the integrand of 9t to the second plus 1 over 3. So let's keep going. Simplify the integrand a little bit. 9t to the second over 3 is just 3t to the second. And then plus 1/3. And then an antiderivative of 3t to the second plus 1/3 is t to the third plus 1/3 t. And then from 1 to 3, so we get 3 to the third is 27 plus 1/3 times 3 is plus 1. And then minus 1 plus 1/3, which is minus 4/3. So 28 minus 4/3 is 26 and 2/3. That's what I got. Okay, on number 6, find the surface area generated by rotating the parametric curve about the x-axis. Okay, the formula for rotating a parametric curve about the x-axis, formula for the surface area, is the definite integral from t equals alpha to t equals beta, 2 pi times y, or g of t if y is g of t, and then times the square root of dx dt squared plus dy dt squared dt. Okay, so we have y, and we can find dy dt, dx dt and dy dt. X is equal to t over, or t plus 1, so dx dt is 1. Dy dt is just 1/2. So we can go ahead and write the integral for the surface area from the integral from t equals 1 to 5, 2 pi times y. Y is t minus 1 over 2. And then we have the square root of 1 squared plus 1/2 squared, or 1 plus 1/4 dt. Okay, 2 pi times t minus 1 over 2. The 2's cancel. Pi is a constant. The square root of 1 plus 1/4 will simplify to the square root of 5 over 2. So if we bring the constant out front, we'll get the square root of 5 times pi over 2, and then the integral of t minus 1 from t equals 1 to 5. Okay, that looks right. So the square root of 5 times pi over 2. And antiderivative, t to the second over 2 minus t from 1 to 5. So when t is 5, we get 25 over 2 minus 5. I'll write that as minus 10 over 2. And then we're going to subtract, when t is 1, 1/2 minus 1, but I'll write that as 1/2 minus 2 over 2. So we get 25 over 2 minus 10 over 2 is 15 over 2. 14 over 2, and then 16 over 2. So this all simplifies to 8. And then 8 divided by 2 is 4. So the answer I get is 4 times the square root of 5 times pi. Okay, let's sketch the polar curve. R equals sine of 2 theta. So before sketching this, or maybe you already did sketch it, what can you say about the polar curve after it's sketched? What's it going to look like? It's going to have 4 loops. But even if you don't know that, if you know the procedure, so what we usually do is sketch the equation in rectangular coordinates first, and then use the rectangular coordinate graph to draw the polar curve. So we're going to go from 0 to 2 pi, but the graph of r equals sine of 2 theta in rectangular coordinates is going to have 2 periods in it. If a different color helps, I'll do that. So we get 2 periods. Hey, notice the first high point occurs at pi over 4, a low point at 3 pi over 4, another high point at 5 pi over 4, and a low point at 7 pi over 4. So if we subdivide the plane, so this is theta equals pi over 4. This one is theta equals 3 pi over 4. Theta equals 5 pi over 4. And theta equals 7 pi over 4. Okay, so at pi over 4, the R value is 1. So it starts at 0, it's 0 and increases to 1. And then it goes back to 0. Between pi over 2 and 3 pi over 2, the R values are negative. So at 3 pi over 2, we go in the opposite direction. Because the R value is negative, so the graph goes to the opposite side of the origin from 3 pi over 4, and then back to 0. At 5 pi over 4, the R value is positive 1 again, so the graph comes out here, and then it goes back to 0 at 3 pi over 2. And then at 7 pi over 4, the R value is negative, so the polar curve goes in the opposite direction from the origin, so the polar curve goes up here. And then back to 0. So 4 loops. Each one of those loops is supposed to be the same size. So okay, the next page. Sketch the polar curve R equals 1 minus cosine of theta. So first we'll sketch the graph of the rectangular coordinates. So this will have 1 period between 0 and 2 pi. Hey, when theta is 0, cosine of 0 is 1, so 1 minus 1 is 0. So we have this point on the graph. At pi over 2, cosine of pi over 2 is 0, so we have the point is at 1. When theta is pi. Cosine of pi is -1, and 1 minus -1 is 2. So I have this value of 2. And at 3 pi over 2, cosine of 3 pi over 2 is 0. 1 minus 0 is 0. And then at 2 pi, cosine of 2 pi is 1. 1 minus 1 is 0. So the graph is going to look something like that. Okay, so what's the polar curve going to look like? When theta is 0, that's the polar axis, the positive x-axis. The r value is 0. And then the r values are small positive numbers, and then at pi over 2, we reach 1. So the curve does something like that. Then by the time it reaches theta equals pi, the r value is 2. So in the pi direction, that's to the left 2 units. So this is a cardioid. So the top half is supposed to be a reflection of the bottom half. By the time we get to 3 pi over 2, the r value is 1, so it's going to do something like this. And then between 3 pi over 2 and 2 pi, the r values get smaller and smaller, and then finally reach 0. That's a cardioid. Okay, the next one, r equals 2 times cosine of theta. This one's in rectangular coordinates, is fairly easy to graph. So the amplitude is 2. Well, we start out at theta equals 0. We get 2, then it's 0 at pi over 2. Hey, what will the polar curve look like this time? Hey, when theta is 0, the r value is 2. So we have this point. At pi over 2, the r value is 0. At theta equals pi, the r value is -2, so we plot a point in the opposite direction. So we plot this point again. At 3 pi over 2, the r value is 0, so we're back to here. And then at 2 pi, we have r equals 2. So I only plotted 2 points. What happens in between? So it's a circle. So how can we verify that from the polar equation? So sometimes that can help. If we multiply both sides of this equation by r, we get r to the second equals 2r cosine of theta. And r squared is x squared plus y squared when we convert it to rectangular coordinates. R cosine of theta is x, so we get x squared plus y squared equals 2x. And this is an equation of a circle. It's not in standard form. We can get it in a standard form if we first subtract 2x from both sides. And then complete the square. We get x squared minus 2x plus 1 plus y squared equals 0 plus 1. And then the standard equation, x minus 1 squared plus y squared equals 1. So the center of our circle is the ordered pair 1, 0. We can see that there, and the radius is 1. Okay, we're out of time. We'll pick up here tomorrow and go ahead and sign in for attendance.